Robert Andrew Millikan was an American physicist during the 1900s. He got the Nobel Prize for Physics in 1923 for his study of the elementary electric charge and the photoelectric effect. Millikan started his experiment to demonstrate the charge carried by a single electron by measuring the cause of charged water droplets in an electric field. However, that experiment was not accurate enough to convince people. In 1910, Millikan came up with a similar experiment, which became his famous experiment and one of the most important experiments in physics, where water was replaced with oil, which led to the discovery of the charge of a single electron. Millikan's apparatus contains a chamber where an atomizer is installed at the top of it. Two plates are positioned parallel to each other. The top one will be the positive electric plate and the bottom one will be a negative electric plate, as shown in the diagram. A microscope is placed to view the region between two plates, as well as a light source to provide a visible view between two plates. To start the experiment, the atomizer sprayed a fine mist of oil droplets into the chamber above the plates. The oil droplets become electrically charged through friction with the nozzle. And ionizing radiation can also be used to ionize the droplets that negatively charge them as they fall down to the plates. As the droplets enter the electric field created by the two plates, they would either slowly fall down to the bottom, get attracted to the top plate, or suspend between the two plates. What Millikan did is to observe the oil droplets and at the same time apply an appropriate amount of voltage so that the oil droplet became stationary between two plates. When the oil drop suspends in the air, it means equilibrium is achieved and the oil drop is now affected by the equivalent force of the gravity and electric field, which gives us this formula, Fe equals to Fg. We know that Fe is equal to Eq, and E can be found by dividing the potential difference by the distance between two plates. Therefore, we have Fe is equal to a Vq on D, where V is the voltage, Q is the charge, and D is the distance. Now let's look at the gravitational force. Fg is equal to mg, where g is the gravitational constant, m is the mass. M can also be expressed as ρv, where ρ is the density of the oil drop and v is the volume. Then we'll get this equation. As mentioned above, Fe is equal to Fg, which leads to this formula. Make Q the subject, then we have the equation for the charge of a single droplet. However, the radius is the only factor that hasn't been found yet. So in order to determine the radius of the droplet, Millikan observed the falling droplet and measured its terminal velocity when electric field equals to 0. At the terminal velocity, the weight is balanced by the viscous air resistance, or drag force. Drag force is given by Stokes' law. Fg equals to 6 pi eta rv, where eta is the viscosity of the air, v is the velocity of the droplet. And because the forces balance each other out, we have Fd equals to Fg. Make R the subject, substitute R back to this equation, we then can determine the charge of a single droplet. After precisely calculating the charge of 58 droplets over the course of 60 consecutive days, when comparing the differences of charge between each droplet, Millikan noticed that some droplets will have the value of 3.2 times 10 to the power of minus 19, others will have 6.4 times 10 to the power of minus 19, which appear to always be a multiple of a certain number, and is 1.6 times 10 to the power of minus 19. As a result, Millikan was then able to determine the charge of the droplet, as well as an electron was always an integral multiple of a minimum charge, which is 1.6 times 10 to the power of minus 19.